Okay, so remember, complex numbers are numbers that have some imaginary component and some real component. So we write them in the form of AI plus B, where I is the imaginary element. And really, it's just a handler for a situation that we really wish we didn't have to deal with. And that's what happens when you try to take the square root of a negative number. So, for example, -1. In the real world, we would never ever try to do that because it's not real, and so we wouldn't deal with it. But the problem is, in many, many different sciences, -1 or the square root of -1 comes up all the time and is real in that world. And so we have to have a way to handle that negative value. So what we call it is, or what we do, is we identify the value of the square root of -1 as I. Now we can handle this, because if the square root of -1 equals I, then we're not actually dealing with negative numbers in our operations, and it all works out nice and neat for us. So let's do a couple of examples real quick. Find the value of I squared. So I squared would just be the square root of -1 being I, and all of that has to be squared. Well, we know the square root and the square of a number, that's inverse operations, they disappear. So I squared equals -1. Now notice what happens. We're dealing in this bizarre weirdo world where we have a value or a way of labeling the square root of -1. That also means that there is a number out there that we can square and get negative answers for it. Okay, so these are imaginary numbers. They're on the imaginary plane. If we try to graph these or work with these, we can't even use the same plane that we're used to using. We have to use a plane where you have an input variable or a domain variable, and then the output is the imaginary plane or the imaginary output. So we can't even use a standard XY plane to work with these numbers, but they're still really fun to play with. So let's find the value now of I cubed. Well, in this case, it's easier just to remember that I equals the square root of -1 and that I squared equals -1. So I have I cubed is I squared times I, which equals -1 times the square root of -1. And so I cubed is just the square root of -1. Or more precisely, -I. Okay, so all we're dealing with right now, though, is dealing with the imaginary element or the imaginary number. But this section is really about, back here where we started, it's really about complex numbers, where you have an imaginary part and a real part. So if you have the number 2i plus 6, this would be, all together, we would call this a complex number. But individually, I can say this is the imaginary part, and this is the real part. Something really cool to notice at this stage is that the real part is really just a number on the real plane, and we know that 0 is a number on the real plane. So the truth is, if I had an imaginary number written in this form, 0i plus 6, well, 0 i's would just be 0. The whole thing would just equal 6. So in a sense, you've been working with complex numbers all your lives. You just don't really know, because when you're dealing with an integer or a number on the real plane, you're really just dealing with a complex number where the coefficient on I is equal to 0. That's just a little factoid. And you may have noticed also that an imaginary number looks an awful lot like a polynomial, right? It looks like you have, if I were an x instead of an I, it would just be a polynomial. And it turns out that we operate these exactly the same way. So let's do a couple of examples to show that. So let's add and subtract complex numbers. I'm just going to subtract. So in this case, I would have a complex number, 5 minus 3i, and plus negative 2 plus 4i. So in this case, notice that it's written opposite than I wrote up here, but it's just like a polynomial. As long as you take the sign with the finger quotes term, as long as you take the sign along with you, you can switch these values around. So adding and subtracting these is exactly the same thing. I'm going to add the integer part or the real part, and then I'm going to add the imaginary part to the imaginary part. Much like on a polynomial, I would add the constants together and then I would add the like terms. So 5 plus negative 2 is, well, let's clear the parentheses first. I have a plus sign out here, so I'm not really concerned about the parentheses on this first one. But I'm going to add a negative 2, which means dropping the parentheses. I just changed the sign, or keep the sign inside and don't make any changes because I have a plus sign, and then plus 4i. So now let's combine them. 5 take away 2 is 3, and negative 3i plus 4 is plus I. And I write them this way. I write them this way where I put the imaginary part in the front. Your textbook is going to write them with the imaginary part in the back. It doesn't really matter to me as long as you make sure you're really careful with the signs, that you take the sign with it. Let's do another example. This time I'm going to multiply. So I'm going to keep the same values. 5 minus 3i, only this time I'm going to multiply it to negative 2 plus 4i. So this is a complex number times a complex number. And all you're going to do is distribute as though it were a polynomial. You have 5 times negative 2 is negative 10. 5 times 4i is plus 20i. Negative 3i times negative 2 is a positive 6i. And then negative 3, now watch this. Negative 3 times positive 4 is a negative 12. I times I is I squared. But what does I squared equal? I squared equals negative 1. So we have to change the sign on that last value here. And we're also going to lose an I in this last term because I squared is negative, so I can cancel that out and change the sign in front. And all I did just now, it's a shorthand step. All I did was I took 12I squared and made that equal to 12 times negative 1, and then made that equal to negative 12. So that changes the sign out here. Or I guess I did it by starting with a negative 12 and then multiplying negative 12 times negative 1, which gives me positive 12. And so that changed the sign of that last, and it really converted it to a coefficient or to a constant. So now let's combine our like terms. So I have 20 plus 6 is 26i, minus 10 plus 12 is plus 2 on the real plane, and so I have 26i plus 2, which is the same thing as 2 plus 26i. Alright, so the place it gets a little bit tricky is when we're dealing with fractions and complex numbers. So if I have the complex number 5 minus 3i divided by 1 minus 2i, if I write it out in fraction form, 5 minus 3i divided by 1 minus 2i, we want to do something. We want to rationalize the denominator in this case. It's much like having a radical in the denominator. We want to kind of simplify this by getting rid of the I in the denominator. And we do it exactly like we would with rationalizing. We make use of the fact that the difference of two squares pattern. So we have, the sum and difference of binomials pattern. So we're going to multiply the denominator by 1 plus 2i, which is the conjugate, right? So this is called the complex conjugate. Okay, and then the same thing in the numerator. Now I can do distribution. The bottom part is easy because this is just a sum and difference of two squares pattern. So I've got 1 times 1 is 1 minus 2i times 2i is 4i squared. That equals a negative 1, so I know my denominator is going to end up just being 5. But what about the numerator? Well, this is just multiplying binomials, so I'm going to use distribution. 5 times 1 is 5. 5 times 2i is plus 10i. Negative 3 times 1 is minus 3i. And negative 3 times 2 is minus 6i squared. I squared is a negative 1, so I can just change that sign, and now I just combine like terms. 10 minus 3 is 7i, and 5 plus 6 is 11. Now, this part, it doesn't matter to me whether you write the i's in the front or the i's in the back, but it does matter. The convention is that we don't keep this 5 in the denominator. We don't keep it written like a rational number. We actually write this as 7i over 5 plus 11 over 5. So we're going to switch it to the a plus bi form, or ai plus b form.